It's a pleasure for me now to introduce our next speaker, Michael Cuffaro from Munich Center for Mathematical Philosophy.
Okay, I want to begin by pointing out that interpretational debates in quantum theory tend to focus on the status of the state vector. So what I mean take an example, see for example the distinction between psiontic and psi-epistemic interpretations of quantum theory. However, I think there are at least prima facie reasons to question the cogency of this focus. For instance, we have Gleason's theorem, which tells us that quantum theory's assignment of probabilities is complete in the sense that every probability measure over yes or no questions concerning the observable quantities associated with the system is representable by means of a density operator acting on the system's Hilbert space. That's not true for state vectors unless, of course, you appeal to a larger Hilbert space, and I'll get into that a little bit later. Quantum mechanics is a probabilistic framework, at least at the phenomenal level. So even if you argue, as Everettians do, that probability assignments aren't fundamental, we think it makes sense to focus your interpretational energy on the density operator. Probability assignments aside, density operators are generally used to represent open systems of quantum theory. And these evolve in more general ways than the closed systems that are represented by state vectors. Now, in a paper that we posted recently on the archive, Stefan Hartmann and myself have argued that open systems represented by density operators should be thought of as fundamental in quantum theory. Now, I also want to point out that Eddie Chen, who's here as well, has argued something similar over the past few years, although for Eddie, if I understand his view correctly, it's the focus is more on the density operator formalism and not as much as it is for us on the connection between density operators and open systems. Something like that. Now, Stefan and I flesh out our claim that we should think of open systems dynamics as fundamental in terms of a framework that we want to call the general quantum theory of open systems, or GT for short, which we distinguish from what we call standard quantum theory. Now, in the general quantum theory of open systems, the physical state of a system in general S is represented by means of a density operator rho. And the time evolution of rho is governed by a dynamical map, lambda sub t, such that if you apply the map lambda sub t to the density operator representing the system at the initial time, you get the density operator at the time t. Now, importantly, lambda t is a map that acts on the state space of S and not on the state space of the system and environment. And also importantly, this dynamical map is going to describe dynamics that's in general non-unitary. Now, in standard quantum theory, of course, you can also describe the dynamics of open systems. However, in standard quantum theory, open systems dynamics must always be viewed as a contraction, which we calculate using the partial trace operation of the dynamics of the system and environment. And these overall dynamics are represented in terms of a unitarily evolving state vector. And so this diagram here, this is what we call the closed systems view. Now, what's important here is that this forces the dynamical map on an open system to be a completely positive map, in the sense that this is an implicit assumption in Steinspring's theorem, as Raggio and Primus in this quote from their 1982 paper explain, which I won't read. In GT, however, open systems are taken to be fundamental. So there's no need to understand open systems dynamics in terms of a contraction of the dynamics of a larger closed system. It follows then that the dynamical maps that govern the dynamical evolution of an open system do not, in general, need to be completely positive. That makes it possible to describe the evolution of the universe as a whole as if it were initially a subsystem of an entangled system. So GT, unlike ST, allows for fundamental non-unitary evolution. And it is in that sense a more general dynamical framework than ST, despite not really adding anything to the Hilbert space formalism of quantum theory. Now, in our paper, Stefan and I argue that GT is a more fundamental theoretical framework than ST. It's a long paper, and I don't want to go through all the detailed arguments here. But before I go on, I want to address what I think is a knee-jerk reaction / objection that I'm sure many of you are thinking of, well, some of you are thinking of right now. And this is the objection that, well, shouldn't the empirical success of standard quantum theory motivate us to take unitarity to be fundamental? Now, our response, which is our take on a suggested line of argument that was suggested to us by Wayne Mervold, is that on the contrary, On the contrary, in practice, strictly speaking, we only ever apply quantum theory to open systems. Those applications are the basis for the empirical success of the theory. And it's only natural to extrapolate from this, we think, in principle to the dynamics of the universe as a whole. So the question I want to address in this talk is, where does this leave the various interpretations of ST? And the two case studies I want to consider are, on the one hand, the Everett interpretation, and on the other hand, the informational interpretation. Now, these two case studies are interesting because both of them take vanilla quantum mechanics as providing the resources with which to completely describe reality. Yet, in terms of their a priori commitments, these two interpretations couldn't be more different. Yet, we want to argue both interpretational families have very good reason to endorse the open systems view of quantum theory. Now, I also have other more self-serving reasons to focus on the informational interpretation as opposed to other ones. And I want to point out these are separate from Stefan's and my arguments for the open systems view. One of the original motivations of this conference was to understand better why the many worlds / Everett interpretation is not the consensus. Since I'm here, and since I've defended the informational interpretation recently, I think it makes sense to take the opportunity to tell you all why I'm not an Everettian, despite being both, on the one hand, a realist, or at least a realist of a kind, that is an empirical, not a transcendental realist, and B, not interested in hidden variables interpretations, except insofar as they illuminate in the way that they quantify how quantum mechanics differs from classical mechanics and other conceivable theoretical frameworks. Now, in order to frame the question, the distinction between these two interpretations of quantum theory that I want to consider, I think it's helpful to consider some of the very important distinctions between classical mechanics and quantum mechanics. So in classical mechanics, specifying a system's state yields an answer to every yes or no question that can be asked about a particular observable quantity. For example, is the value of this observable quantity A within the range delta? Observable quantity related to a system. Now, the classical state is a truth maker for that observable in the sense that it determines the answer to every yes or no question about the quantity, irrespective of how we interact with the system. Moreover, that's simultaneously true of all observables in the sense that the state determines the answers to all questions concerning all observable quantities in advance. Now, in standard quantum theory, or quantum theory in general, states fail to be truth makers in two senses. So the first sense is what Itamar Petovsky, I think he was the first one to coin this term, in 2006 called the big measurement problem. And this is the problem that specifying the state vector psi yields in general only the probability that the answer to a given experimental question will take on a given value. Now, I just want to point out that that's not as much of a departure from classicality as one might think, because conditional on the selection of a particular observable, the observed statistics are going to be describable by a classical probability distribution. Yet the other sense in which in standard quantum theory states fail to be truth makers is what Petovsky referred to as the small measurement problem. And this is the problem that the classical probability distributions that are associated with the individual observables cannot be embedded into a global classical probability distribution over all observables. In standard quantum theory, one can only say that conditional upon inquiring about the observable A, that there's going to be a particular probability distribution that one can use to characterize the possible answers to that question. Yet ST's unitary description of a measurement interaction does not by itself prefer any one of these. And so for Everett, that's known as the preferred basis problem. Now, speaking of Everett, so for the Everett interpretation, the Everett interpretation subscribes, in the way that I understand it, subscribes to what I want to call the traditional metaphysical picture, or maybe a received view would have been is a better way of putting this. And on a position like this, that dynamical variables like position, momentum, the direction of a particle's spin, and so on, are understood as manifestations of an underlying reality whose properties are such as to give rise to the values of the observable quantities that are revealed in our experiments with physical systems. I think Tim Maudlin said something similar yesterday. But since the values of the observable dynamical quantities as described by quantum theory cannot actually be consistently interpreted because of the big and the small measurement problems as representing determinate properties of a single classically describable physical system, And since physical reality is, on the Everett interpretation, completely described by the quantum mechanical state vector, the most natural thing to say, and I say that sincerely, is that at least in principle, all of the approximately classical possibilities described by the state vector are physically realized. So let's move on to the informational interpretation. And here I'm going to be drawing mostly on this book that I recently published with my co-authors, Michael Janis at the left and Michelle Janssen at the right. Though I want to point out that our view is very similar to views that have been defended over the years by Itamar Potovsky as long ago as 1989, Czeslaw Bruckner and Anton Zeilinger, Jeffrey Boob. In fact, Jeff wrote the foreword to our book, and Bill Demopoulos, among others. Now, the informational interpretation, I think this is important to point out, isn't opposed to the traditional metaphysical picture per se. This picture would be apt, for instance, if classical mechanics were fundamental. At least this is the way we think of it. But we are also open to the possibility that it is not apt. Because for us, how we carve nature at the joints is something that should be motivated, or at least connected with physical theory. Now, the position is not an anti-realist position, because the question isn't whether, but how to assign physical properties to what we take to be the external world. In other words, what's taken as primary is not the traditional metaphysical picture. Rather, it's the empiricist methodology through which we reason from the values revealed in experiments, carried out under precisely specified experimental conditions, to a picture of the world which doesn't transcend those values, but is anchored in them. In other words, to put it a bit more formally, probabilities are essentially conditional probabilities for an informational interpreter. And the picture that our theories build up of the world is, in this sense, essentially a contextual picture. Although, of course, it can admit of special cases, of which classical theory is one. That is because the probability distributions over the values of every classical observable are determined independently of whether a physical interaction through which one can assess those values is actually made. We are invited to think of them as originating in the properties of an underlying physical system that exists in a particular way, irrespective of anything external. As for quantum theory, the more complex structure of observables related by quantum theory doesn't similarly invite the inference from the values of observable quantities to the properties of an underlying system in that sense. What is exhibited by the quantum state on an informational interpretation is not a collection of observer-independent properties, but the structure of and interdependencies among the unitarily related possible ways that one can effectively characterize a system in the context of physical interaction. And I refer to Curiel here because that's exactly the way he characterizes an abstract classical system in the context of Lagrangian mechanics. Now, you might object, can nothing really be said about what the world is like independently of observation on such an interpretation? On the contrary, on the one hand, we have non-dynamical quantities like mass, spin, charge, and so on, for which the assignments of values to those quantities are going to be valid regardless of the experimental context. As for dynamical quantities, on the informational interpretation, the world is such that all of the effectively, approximately classical pictures that one can draw of it under the precisely specified experimental conditions that correspond to each of them are precisely relatable to one another in the way described by quantum mechanics. That's not a trivial thing, according to us. Now you might ask, does B depend physically or metaphysically on the existence of conscious observers? No, absolutely not. All that's happening here is that a schematic representation of what relevantly constitutes an observer, a classical conditional probability distribution, also referred to by informational interpreters, especially Jeff Boob, as a Boolean frame, is being used as a formal tool with which to describe how the various possibilities that are implicit in the world are necessarily related to one another. So it's a structural view, essentially. Now, of course, the world isn't being described here as if it were a substance that exists in itself in the traditional metaphysical sense. But on the empiricist perspective that's embraced by the informational interpreter, we were never committed to that anyway. Although we don't rule out that such a picture is apt. Physics is in the business of describing, for the informational interpreter, in accordance with this empiricist methodology, the true empirical relations that obtain in the world. So, to come back to the question of open systems now. When we're presented with a system in a state vector psi that's decomposable into some particular basis B1, which is unitarily related to some particular basis B2, what does that mean for an informational interpreter? Well, it means that coupling the degrees of freedom of the system S to those of a further system M, will yield a collection of unitarily related conditional probability distributions over the possible outcomes of an assessment of M as described with respect to a particular basis Bm. And I won't read the Bohr quote, but I think that's essentially what Bohr's saying in different language. So notice here, right, that S is conceived as an open system, even when we describe it stated by using a state vector. But since open systems dynamics are not fundamental in ST, which is something I said at the very beginning, we require a larger Hilbert space, which includes the degrees of freedom of both S and M to represent it as such. That's true regardless of the level of analysis or of scale, even when S is the whole universe. There's no question of taking either the state vector, psi S plus M, or the density operator, rho S, to truly represent a closed system of observer-independent properties. Standard quantum theory is about open systems on the informational interpretation, despite being formulated from the closed systems view, which it inherits from classical mechanics. So the motivation for adopting the general quantum theory of open systems, which takes open systems to be fundamental, to be our fundamental theoretical framework for describing quantum reality, is very clear on the informational interpretation. So how about Everett? Well, okay, as we're all aware of, Everett, when confronted with a system in a superposition like this, Everett solves the big measurement problem, the problem that ST is irreducibly probabilistic, by asserting that all of the possible outcomes actually obtain. To solve the small, also known as the preferred basis problem, we appeal to the dynamical process of decoherence. When S interacts with another system M, which might include the degrees of freedom of a human agent, the terms in the above superposition for S begin to decohere with respect to a given basis for the density operator characterizing M. Now, an agent whose degrees of freedom are included in M will observe a particular statistical distribution over the outcome, say B1 plus and B1 minus, in agreement with predictions given by the density operator corresponding to the system S. And all of this is determined by the universal state vector psi S plus M. So the properties of closed systems as described by the state vector are certainly part of the ontology of ST on the Everett interpretation. But what about the properties of open systems as described by the density operator? Well, I think, as we've discussed a little bit over the past couple of days, the answer is yes. I mean, so here I would appeal to Wallace and Timpson's article on space-time state realism, which essentially says something like this, I think. We can also appeal to put it in more general terms, which I think is consistent with that. But so more general terms, just looking at the mathematical framework of quantum theory, we know that corresponding to any given probability distribution over the pure states of B, that is, to any given density operator for B, one can always find a pure state of some larger system A plus B from which that probability distribution can be derived. Moreover, all such purifications are essentially the same insofar as they're unitarily related to one another. So rho S, expressed as a decoherent mixture of various states corresponding to the elements of an eigenbasis of rho M, is just as objective a description of everything there is, relative to the degrees of freedom included in a representation of S and to the given eigenbasis as the universal state vector psi S plus M. Now, unlike on the informational interpretation, closed systems represented by state vectors in ST are not intrinsically abstract. At least in principle, they can represent the observer-independent properties of physical systems. Nevertheless, it's clear that the states of open systems are real features of the world, at least on the Everett interpretation. But what about the universe as a whole, you might ask, right? So mustn't it, for Everett, necessarily be described in terms of a unitarily evolving pure state? And if that's so, then wouldn't that entail that we should privilege ST over GT? Well, apparently not, at least not on all versions of Everett. So David Wallace, in his 2012 book, argues, we think convincingly, that it's not inconsistent with Everett to represent the universe in terms of a non-unitarily evolving density operator. And whether we do so or not depends on the available evidence. Now, Wallace's opinion about that evidence has shifted over the years. Nevertheless, the first part of what I said, that it's not inconsistent, I think that holds. I think that's true. And we should be, if we're in Everettian, we should be open to the idea that evidence might change. Sean Carroll, more recently, in 2021, and I quote, writes, technically the state of the universe is more likely to be a mixed state described by the density operator. And I forget the title of that paper, but anyway, I think the title of the paper is something like "State vector is a representation of reality," and therefore it's kind of ironic that he has this quote in there. But anyway, now that might all be true, but there's a prima facie tension, you might think, right? So isn't unitarity required for quasi-independently evolving worlds? And I think, yeah, there is a bit of a tension, but I think we can resolve it. So this is our suggestion. Our suggestion is to take the purification to a state vector in a larger Hilbert space of the universal density operator to be non-fundamental, just like the worlds that it encodes, because worlds aren't fundamental on the Everett interpretation anyway, right? Worlds are real. Worlds are thought of as real, and I think if you buy into the Everettian assumptions, I think legitimately thought of as real, even despite not being fundamental. And I think if you take the universe to be described, dynamics to be described as a universal, as a density operator, you can still think the Brownian structure to be real, even if you don't think of it as fundamental. You know, as long as there are compelling pragmatic reasons for doing so. And here I appeal to the kind of considerations that David Wallace appeals to in his 2003 paper. So we just need to say here that both the branching structure and the worlds aren't fundamental, that their role is fundamentally explanatory, and that licenses us to think of them as real. So the upshot here is that there are good reasons, we think, for an Everettian to at least be open to the idea that the universe could be describable in terms of an in-principle non-unitarily evolving density level. And since this is how one in general describes the dynamics of open systems, there are good reasons to view the dynamics of open systems to be fundamental in quantum theory for an Everettian. So in summary, on the informational interpretation, open systems dynamics are fundamental, that's clear. Closed systems dynamics are an abstract formal descriptive device that we use to get around the fact that ST is formulated in accordance with the closed systems view, which it inherits from classical mechanics. On the Everett interpretation, open systems dynamics are more general, and there's no reason in principle why they can't be applied to the universe as a whole, consistently with the Everett interpretation. We don't think so, as we think so. So it'll depend on the evidence. If and when such evidence is obtained, an Everettian should be open to it rather than be dogmatic. So in summary, we think that both Everett and the informational interpretation have a clear motivation to embrace the general quantum theory of open systems to be a more fundamental theoretical framework than standard quantum theory. Now, very last slide, I just want to point out that although I focus on the informational interpretation, I think that much of what I said about that interpretation could also have been said about cubism, Richard Healy's pragmatist view. I'm a little less sure now, as I used to be, about Carlo Rovelli's relational view, but I think it probably applies there as well. Now, you might be wondering, though, about hidden variables interpretation. So I think that in that case, GT is probably unlikely to satisfy those who advocate for them, because GT shares some of the features of that hidden variables theory's proponents find objectionable in standard quantum theory. Nevertheless, since nevertheless, since we want to claim that I've successfully argued that GT is a more fundamental framework than ST, for anyone who interprets ST as complete, it would seem to follow that advocates of hidden variable theories should focus on providing an underlying ontology for GT, not so much for ST. And with that, I want to end.
Thank you. That was a really lovely talk, very interesting. I'm not persuaded, but just on one point, Wayne Merville's comment, which you're taking up, that in fact, all applications of quantum mechanics are to open systems. I mean, there are the cosmological applications, but sure, let's put those to one side. But I think all of the applications of quantum mechanics to real physical systems either treats them as isolated or treats them as embedded in an environment, in which case it's tracing out the environment. So it's not that one starts with, one of these general master equations, and that's what's worked in practice. No, what's worked in practice is either pretending the hydrogen atom is in an empty universe, or just with radiation, or acknowledging the environment and tracing it out. That's what's worked in practice.
Well, I mean, so I see that, but nevertheless, I mean, strictly speaking, the systems that we apply this framework to are open systems in a strict sense. Right. So the systems that we apply this framework of standard quantum theory to are strictly speaking open systems because you can't shield the environment. And given that the general quantum theory is just as descriptive vis-a-vis those systems as standard quantum theory, it seems to me that there's a clear motivation to make that general move to the more descriptive framework.
Thank you for your talk. Just a short question. Please, could you explain more how to understand the reality of the variety world? Because you said they are real if there are pragmatic reasons to believe that they are real. Is it, in my talk, I told that they are real, but their reality is contextual. I also told that cubism, a relational interpretation, could be reinterpreted in this sense, in the sense of the contextual realism. I don't know if you heard my talk.
Was that on Monday? I wasn't here on Monday. I'm sorry.
About the reality of the variety worlds, in which sense they are real, if there are the pragmatic reasons to believe, you said.
So is this a slide that you're referring to? And so, well, I mean, part of the motivation for positing worlds on the Everett interpretation is because worlds are supposed to behave. I mean, as far as I understand it, I'm not an Everettian, of course, but as far as I understand it, the motivation for positing multiple worlds is that, I mean, these, when you look at a given decomposition of the state vector, what you see are things that can be approximately classically describable to a certain to effectively classically describable to a certain approximation. And now that's very useful from a pragmatic perspective, in the sense that it helps to make sense of our experience for an Everettian. Now, given that you have a non-unitarily evolving universe, right, then you no longer have this nice branching structure, and you no longer have these nice approximately classical worlds that you can appeal to. However, quantum theory allows us to purify that state, and so you don't necessarily believe that purification, that abstract purification, is a real thing necessarily, because you've already committed yourself, because you've already committed yourself to thinking of the universe as evolving non-unitarily, at least given whatever available evidence leads you to believe that. But you can still appeal to this abstract purification as an explanatory device, right? And so you can purify the mixed state of the universe, and then such that it exhibits this branching structure, which manifests itself in these approximately classically describable worlds that evolve unitarily. And so that's the idea. It's artificial in a way, but it's nevertheless, the motivation here is not any different, I don't think, or we don't think, than the motivation is for positing the worlds in the first place, which is essentially because it's useful, perhaps even indispensable for physics for making sense of the physical world for an Everettian. So, I mean, I don't share that motivation because I'm not an Everettian, but I think Stefan and I think that that's in line with Everettian motivations.
It's sort of a related question. I mean, I'm wondering what the problem is. If I buy the overall framework here, what the problem is in just defining my branching structure directly off the mixed state. I mean, if I think that I find the conceptually cleanest way to get at the branching structure is through something like a Degean histories formalism. And there's no problem with saying that my quantum state in the Degean histories formalism is mixed. The framework, it works just as well with a mixed state as a pure state. If anything, my worry is you'll get decoherence too cheaply because you can build it in explicitly to your non-unitary evolution operators. But there's no problem as far as I can see in just formally deriving a branching structure from a mixed quantum state.
Well, if that's the case, then that's better for us.
Yeah, I was going to say,
to be honest, right? So I'd like to talk to you a bit more about that afterwards, if you think that's true. Yeah. There's a question right there.
Thank you for your talk. So just kind of to echo David's point earlier first, that So Eugene Chua and I worked on a paper about branching and Born rule for a mixed state Everett and multiverse. So if you're interested, I can send you a draft showing some toy models and toy examples of how you can have branching and decoherence and all of that in a mixed multiverse. And regarding the last slide of your talk, just want to kind of say in support of your position here. I think I like to advocate a density matrix realism, but not going as far as you and Stefan do for non-unitary evolution. But I think for all interpretations of quantum mechanics, Everettian, non-Everettian, GRW, or Bohmian mechanics, they can all be compatible with what you call GT here. So for example, Valiant and co-authors in 2012, I believe, had a paper about a Bohmian theory with stochastic jumpy wave functions. So you can have non-unitary evolution of the wave function guiding the particle motions. And you can also have non-unitary evolution of density matrix guiding particle motions. So all of them are compatible with the basic point here. That is, you can have non-unitarity and density matrix realism, and also compatibility with all major solutions to measurement problem.
Thank you. Yeah, let's talk about that as well.
Just a comment, or maybe just for me, the main reason for many words, it's solution of a measurement problem. And in measurement, it looks like it's not unitary. And the whole idea is to keep the word unitary. So this is, if we talk about motivation, that the whole story of Everett, it's to keep unitarity and linearity. And so,
I mean, thanks. I mean, maybe that strikes a bit more to what I should have said when I made this point here about this prima facie tension. Maybe I should have put it more in the way that you put it, because yeah, I mean what I was trying to get at is there is a tension between non-unitarity and Everett. However one wants to catch that out, right? And our solution or our suggestion is essentially to take the branching structure to be non-fundamental. So even if you have a non-unitarily evolving mixed state, you can purify that state. And you can think of that purification, which is abstract, admittedly, but it plays an explanatory role. And it plays the same explanatory role we think that you would like it to play vis-a-vis the measurement problem. At least that's our claim.
I would just, when Eddie proposed his density matrices, I'll say, I purify it, and then we'll have simpler system for pure state. So, and you suggest me, no, just kind of take density matrix as fundamental, then purify and understand it in every terms. Am I understand your suggestion correctly?
Yeah, something like that. I mean, something like that. I mean, the thing is, like, I mean, if you have evidence that the universe is evolving non-unitarily, for whatever that evidence might be, then we fail to see why one should be dogmatic and insist that really we should describe it as in terms of a unitarily evolving pure state. Nevertheless, one can still insist on that, but just as long as one is willing to admit that when one does that, it's for explanatory reasons and not for fundamental reasons. And that's all. That's what our suggestion amounts to.
Not obvious that we can purify every non-unitary evolution.
Right. You can't purify a non-unitary evolution that's described by a not completely positive map in particular. That's true. That's true, because when you try to do that to a not completely positive map, you get an overall system that in a certain sense is unphysical, because if you try to perform joint experiments on the system and environment, you'll get negative probabilities for some experiments, and that makes the environment in that case even more fictitious. Nevertheless, you can still see it as played an explanatory role, even if you don't take it seriously. It's just even more motivation to take it as non-fundamental, but as explanatory. I don't mean that as a criticism of it. I don't think that's inconsistent with the motivations of Everett in the first place.
Can you say something more about the Boolean frame you hinted at? As far as I understand, it's a way to make sense of conditional probabilities, but do you have a physical way of defining? How do you define it exactly?
Well, in a given experimental context, there are a number of observables that are compatible with one another, right? And so we can impose what you might call a Boolean frame, right? Which essentially tells us, for this question we get the answer yes, for this question we get the answer no, and so on. And so the Boolean frames that correspond to each experimental context in quantum mechanics aren't consistent with aren't compatible with one another. It's just non-commutativity. Right. And so that's all we mean.
So it's basically fixing the observables related to a given experiment.
Nevertheless, they're relatable in a precise way that's described by quantum mechanics.
Right. Thank you very much.
Time for one last question. I'll take it from Carlos. Yes.
Thank you for the nice talk. Thanks for the talk. So I'd like to, just have your input on it. You know very well that we have systems obeying non-unitary dynamics, but in each single case that we have that, we can think of that non-unitary dynamics as being explained by coupling with a larger system, and that whole system evolves unitarily, but we actually witness this larger system and we can trace it, like, oh, it was the microwave background, or it was that particle, it was, the first electron of the cascade of reaction that amplified the signal. We actually have, the whole theory. It's not just as if there is a reaction that is overall unitary. So don't you find it somehow fine-tuned that to postulate non-unitary dynamics as fundamental, but it just so happens that we have never yet observed a system evolving non-unitarily by itself?
Have we ever observed a closed system? It comes back to Simon's question, I guess. Yes, we apply the framework of standard quantum theory, which brings with it this closed systems view that I mentioned. But have we ever, strictly speaking, observed a closed system aside from the universe as a whole? And even then, so it just comes back to that same point. And I can only answer what I answered to Simon, is that strictly speaking, these physical systems that we apply the standard quantum theory to, which brings with it the closed systems view, are strictly speaking not isolated. Even if we're able to treat them as isolated, right? Successfully. I'm not saying that's not successful. Even though we're able to treat them as isolated, given standard quantum theory, strictly speaking, they're not isolated. Right.
Yeah, but again, gravity is also, we also have it in the story. So if ever gravity is, for example, decohering systems, we know where the witness is, so we know where the information is gone.
I'm not denying that. I'm not denying that the standard quantum theory is successful in exactly the sense that you're describing. Nevertheless, the systems that we actually apply quantum systems to, really are open systems. And so it makes sense to at least consider generalizing the dynamics of open systems, and just in the way that Newton thought that we should generalize as far as we can until we get this improving evidence. Maybe we should do that in this case too.